think around the same target, the same stuff, but you're done with that. So we're EC 590 today, and the first speaker of the day is Xiaolong Zhang. She's working with Professor Kiruba Haran, and the presentation topic is it will compare the decoupling synchronous current PI regulators for high-speed current synchronous drives. Please welcome Xiaolong.
Thank you. Hello, everyone. Thank you for coming. And today I'm going to talk about a comparative study on the decoupling synchronous current regulators. This is an outline. First, I will introduce the background, and then the basic modeling and analysis method for the regulation system, and then the different options for the decoupler designs, and then the influence of delay, and then some design guidelines. So high-speed PM machines can achieve high specific power, which makes them good candidates in aircraft electric propulsion system applications. And to make its application practical, we also need to have a power electronics converter to control it, to do a speed regulation. And for the speed regulation, we also want to control the inner loop current dynamics. So that's what this study is about. And for the synchronous current PI regulator design, it needs to take into account the DQ axis coupling, inductance variation, and the sampling delay. And this picture shows a general structure of the PMSM digital drive system. You can see that there are two loops, an outside speed regulation loop and an innermost current regulation loop. So to make the outer loop fast and effective, we need the inner loop to have a very high bandwidth and to be stable as well. Okay, so when we study the electrical subsystem model, we can see it can be expressed as a matrix form, and the D and the Q axis, they have a coupling term between each other. And then this is a current feedback control system block diagram. So basically, the plant is in stationary reference frame, but the controller is normally implemented in the synchronous reference frame. So there will be a inverse Phuc and a Phuc transformation that link between them. To perform the analysis, we need to convert all the model into one unified reference frame. So when you convert it to the same unified synchronous reference frame, you got this block diagram showing here. And the current regulator, we assume for now it is just a classical proportional integral controller. And then you got the transfer function for the total system. So in here, the input and output are expressed as a complex state variable. So this variable actually comprises both d-axis and the q-axis current. So the d-axis is the real part of the variable, and the q-axis current is the imaginary part of the variable. So this transfer function is actually a little bit different from the conventional transfer function that we normally know, because you see that the some coefficients have an imaginary part in it. But we can use the well-known methods to analyze this transfer function, like the Bow diagram. And you can see that this system will not be just a normal secondary order system. Actually, it behaves like a fourth order system. So it's a high order system, and it's hard to use just the normal second order system characteristics to analyze it. So you use closed form ball diagram to analyze it, and we use the resonant peak and the frequency corresponding to that peak to indicate the stability and the bandwidth. So we can calculate the poles and the zeros for this system, and this plot the root locus of this system. And you can see that there are 2 poles and 1 zero. One of the poles has a low frequency, it's corresponding to the plant model, and the other has is a high frequency, corresponding to the controller pole, and a controller 0 that we place it arbitrarily, but normally the strategy is to place the controller 0 close to the low frequency pole, so that the low frequency pole and the 0 are cancelled out, and what's left out is the high frequency pole, so that we get a high bandwidth response. That's the basic strategy. However, looking at the root locus, when the rotor speed increases, which corresponding to the increase of a synchronous frequency, you can see the high frequency pole will move towards the origin, and it's drifted far away from the placed controller 0. And then the pole 0 cancellation is not effectively achieved at high speeds. So when you perform an inverse Laplace transform to the model, you can see you got the step response of the system, and you can see that there are 2 modes, 2 model components show up in the resultant step response. So you can clearly see the effects of the cross-axis coupling that leads to a performance deterioration in the high speeds. And then this is a comparative study table that shows how the dynamic performance change with the change of speed or change of the controller gain. So the fundamental frequency increased from 0 to 600, and also some other variation of the controller gain, because the Kp and the Ki, their ratio are fixed to do the pole cancellation, but a global gain can be still changed. We can see that as the speed increases, the performance deteriorates, because the percent overshoot increase and the rise time increase as well. And as the controller gain increases, the performance improves. The overshoot decreases, and the rise time decreases as well. So you can see the influence of speed is not very good, but adding some controller gain, we can improve the performance backwards. So there are 2 things that we can do. One is to reduce the speed-dependent effects. The other thing is to achieve the highest gain as possible, but later we will see that there is a limit on the high gain that you can achieve, because too high a gain that will lead to an unstable operation. So how do you reduce the speed-dependent effects? That's through some design of the decouplers. When we express this system function in this form, we can see that this imaginary coefficient is actually the coupling path between the d and the q axis. So if we add another term that can cancel this, the effects of this path, we can hopefully achieve some performance that are unaffected by the speed. And this picture shows the response of a synchronous frequency at 600 Hertz compared to this response at 200 Hertz. We can see that a higher percentage overshoot and a higher rise time is shows up because of the higher fundamental frequency. So there are three types of decouplers that we can utilize. One is called a feed-forward decoupling PI controller. In this one, that we use the reference current and multiply with this reactance factor and add it to here, so as to cancel this this coupling path. And the corresponding transfer function is here, that we can show that it's actually adding an imaginary component on the denominator, so that the effect can be reduced. The other coupler is feedback decoupling, that we use the measured current to detract it from the coupling term, and we got this transfer function. The other thing is to actually modify the vector PI controller to make it to make the coefficient of the Kp and Ki plus a imaginary component, and so that we actually place the zero not only on the real axis, but also has an imaginary part in this placed zero. And then we got this this transfer function for complex vector PI controller. So you can also got the root locus with varying synchronous frequency. So this root locus is not by varying the gain. Instead, it's by varying the speed, rotor speed, or synchronous frequency. And we can see that in the first feed-forward decoupling, the zero will move along with the pole, so that the low speed, the low frequency pole tend to be reduced, its effect. And in the second one, actually, it cancels out the movement of the low frequency pole and the high frequency pole. And in the third one, it's the zero actually moves on top of the zero will be on top of the plant pole, so that this pole is also cancelled out. And then through numerical simulations built in Simulink, we can see the effects. So without the decoupler, previously we can see that the decoupler, the rise time is 11 milliseconds, and the percentage overshoot is 35%. And then using these three decouplers, we reduce the rise time to 0.3, 1.7, and 1.9 millisecond. So in this case, the feed-forward decoupler achieves the highest bandwidth, and the other two decouplers achieve similar performance to the system at the zero speed. All these simulations are done at the 600 Hertz. And the overshoot peak, for the overshoot peak, the feed-forward decoupler has a 30% overshoot, but the other two has almost minimal overshoot. So the feed-forward decoupling has a highest bandwidth, but still high overshoot. But the other two achieves similar performance to the system at zero speed. Another consideration for this decoupler design is we use a reactance factor to multiply with some current feedback to build the controller, and then we know that the machine is a magnetic device, and their magnetic saturation can vary at different operating points. So the inductance can vary over time. So these decouplers need to have be relatively robust to the inductance variation. And this table shows their sensitivities to the inductance variation. For example, this is the one with no decoupler, and the feed-forward decoupler, the inductance variation change from negative 20% to 0 to plus 20%. And we can see that the overshoot is quite sensitive to the inductance variation. And for the feedback decoupler, the bandwidth and the overshoot are the bandwidth is still quite sensitive to the inductance variation, but the overshoot are kept generally low compared to the feed-forward decouplers. And for the complex vector decouplers, we can see that this system is almost insensitive to the inductance variation. So when we choose different types of decouplers, we need to take into consideration these practical effects. Okay. About the gain tuning, we see that the high gain achieves better performance, but with that modeling, we didn't take delay time into consideration. But in fact, we have delay time in the digital control, which is typically one sampling period. And for the PW realization, we also add a half period delay into the system. So the total delay time is actually 1.5 times the sampling period. And then we use pedal approximation to get a rationalization of the delay function. And then we got this transfer function that accounting for that takes delay into consideration. We can see that this is a system response without delay modeled, and this dashed line is the analytical results, and the solid line is the numerical simulation. We see that the analytical doesn't capture a high frequency component in the system response when the delay because of the absence of the delay in the function. And when we with the delay modeled, these curves are almost on top of each other because the delay effects is captured. Okay, with the delay captured, we see that the pedal approximation function actually adds 1 0 and a 1 pole into the system transfer function, and this is actually the pole that introduced by the delay. We can see that it moves rightwards as the frequency goes up. So it means it causes the system to have a probability to get into an unstable operation condition, especially for high delay. So the left figure is a sampling frequency at 10 kilohertz, and this one is 5 kilohertz. So this one, the right-hand figure has a higher delay time because a lower sampling frequency. And we can see that this pole is shift rightwards to and approaching the right half plane, and especially at the 600 hertz, the pole enters into the right half plane, which indicates a unstable operation. So the current step response with 10 kilohertz and 5 kilohertz sampling frequencies shows on the left figure and the right figure. We can see that when the sampling frequency is 10 kilohertz, this system experiences a fast transient at the first like a few milliseconds, but eventually it converges into a stable operation. But in the second figure, it just explode because of the high delay time. So this indicates that the gain tuning need to take into consideration of this effect. We need to when the system has a risk of instability, we need to lower the gain. So with these observations and characterization modeling techniques, we can get a design and a tuning guidelines for a synchronous PI regulator design. First, we need to determine the machine and the drive parameters like the reactance and the inductance and the resistance, and also the switching frequency is a key parameter for our design. And then we can select a decoupling strategy based on the comparative study, and then the system transfer function can be derived. And then we can, oh yeah, I skipped one thing, is that the frequency domain parameters is actually closely related to the time domain parameters that previously in that table, we can see that this bandwidth is closely related to the rise time, and the resonant peak is closely related to the overshoot. You can see a clearly positive correlation between them. So you determine the frequency domain parameters based on the time domain specifications, and then you select the gain pair ratio according to your circuit parameters. And now the goal is to find the optimal gain K that meets the requirement. And then you plot the rule locus with varying K to find a stability region for K. And then you can choose a K that best give a best optimal MP and omega P, the frequency domain parameters that best meet your specifications. And then with this K, you can check the system performance. So this is a quick experimental validation with this ThinkApp PM motor setup. It's the TI box is just below 1 kilowatt. So I run this motor to 600 hertz, and the parameters are tuned according to the guideline I just described, and this step response is obtained. It matched the analytical predictions, and a 3 milliseconds rise time and a 5% overshoot is obtained. So in this talk, we can see that the synchronous current PI regulator design plays an important role in realizing the high-speed PMSM speed regulation system. And then the classical control theory provides effective tools like Laplace transform, rule locus, Bow diagram can all be used to analyze the system. If we modeling the electrical dynamics via complex state variables. And then as the rotating speed of the machine increases, the dynamic performance deteriorates because of the cross-axis coupling effects. And the three types of decouplers can be introduced to reduce the speed-dependent coupling effects. They all have different pros and cons, and also some are sensitive to the inductance variations we need to pay attention to. And the sampling delay in the system can lead to instability, and that places a limit on the maximum gain that we can use for the system. And a 1 kilowatt motor drive system has been set up, and experimental results validated the method. So I'd like to thank the NASA Glenn Research Center and Granger Center for Electromachinery and Electromechanics for their support in my research. And that's my presentation today. Thank you all.
Yes. Question. So it seems to me from the presentation that the complex PI controller has the best performance
Yes.
compared to the other two. So
Yes.
can you comment on the reason why does it provide that superior performance? And is it harder to implement that type of controller compared to the other two? And the second question would be, can you comment, do you do any work on evaluation the effects of the resistance variation on the performance of the controller, in addition to the inductance variation? Because in the motor, when it operates, it may heat up and the resistance may change. Curiously, how would it affect the performance?
Yes, those are all very good questions. The first one, so this comparison, I will say, it from the inductance sensitivity perspective, the complex vector Pi is the best among the three of them. But there were also other considerations which I actually haven't included into this comparison, such as the disturbance rejection. Because I think one paper I read suggests that this controller is worse in that perspective. But it's absolutely not hard to implement. It's not hard to implement. The implementation are almost similar to all three decouplers. Yes, so that one can be used actually. I think some researchers do use that. So you really need to evaluate your system. Is it a you worry more about the inductance variation or the additional current harmonics or other disturbances that can affect your system performance. So, and for the resistance change, I haven't been able to perform an analysis on that because first thing is less severe than the inductance variation, because inductance variation it's hard to predict sometimes, and it's a very non-linear. But the resistance, actually, you have a good method to estimate it online. So even though it could be cause a performance deterioration, but if you're able to estimate it online, you can online change your controller parameters to do it. But I do believe that it will have a if those compensations are not implemented, it will have an influence on the system performance, but perhaps not on the decouplers, because decouplers, they are caused mainly by the reactive voltage feedback. If you look at the coupling terms and the decoupling terms, it's a reactance factor coefficient, but your PI controller tuning is based on your ratio of RS and LS. So it determines actually your global gain in the system. So that really needs to be accounted for when you are in operation, like online estimation of the resistance.
One more question, Xiaolong.
Yeah.
I'm still trying to go to your slide 7. I'm still trying to wrap my head about your transfer function, slide 7.
Yes.
What does a complex transfer function mean? Like, what is J omega E LS S? I'm still trying to figure that out. What does this transfer function mean? Yeah. I've never seen a transfer function like that.
So
S is J omega in frequency domain. So the
yes.
way we go to Laplace transform, S becomes J omega.
Yes.
What is this J omega E?
So you can interpret it as a constant phase shifter, because when you say S equal to J omega, the omega is a variable, right? It means if I apply a sinusoidal excitation, and you got an output, so that excitation is any frequency. That's S equal to J omega, right? So it's a indication of your input function, but in here, it's omega E, so it's corresponding to your synchronous frequency. It's like.
But that synchronous frequency is a state variable itself.
It's a for this study, you view it as a constant, like a for a certain operating point, it's a constant. It's
But then is this cross coupling ultimately you're going to pick ID and IQ separately such that j omega e doesn't exist? Because those IDQ are also imaginary quantities.
Yes. So these two are vectors, right?
Right. So they have real part and imaginary part.
Yes. So when you got this transfer function, for example, for a certain input excitation, sinusoidal excitation, you replace S with J omega.
No, we don't. Okay, do we have still time, or I don't want to. Okay, let's talk offline.
Yeah.
Understand, like, I think you are trying to introduce a nonlinearity into your transfer function, which is kind of where I'm getting bothered a little bit. So your j omega e is a nonlinearity in the system. It's because of if I write the state metric or the state variable form of this entire operation.
I think it's still linear, but it's just it's not just for example, if just a real coefficient, it's just a scalar, right? If it's just a real number coefficient, it's just a scalar that exaggerates or reduces. But if it's a complex number, it's also a phase shifter. But it's still a linear transformation.
Okay, let me think.
Yeah. We can talk later. Thank you.
So hello everyone, thank you for joining my presentation today. And before I start, I would like to acknowledge my co-author and my advisor, Samira Turage and Professor Arijit Banerjee for helping me through the process. I also want to acknowledge the Granger Center for Electric Machinery and Electromechanics, as well as the Advanced Research Projects Agency for the financial support. So in this talk today, I will present the maximum power point tracking for an integrated generator-rectifier system. And the application we are looking at now is in offshore wind turbine. So first, let me try to motivate why we're looking into the offshore wind turbine. So moving forward to the future, we want to have a neutral carbon economy. And going to the renewable resources is the way to go. And if we look at the capacity of the offshore wind turbine, it is estimated to produce twice the amount of energy that need by the US. And the offshore wind energy is distributed along the coast, like on the East Coast, the West Coast, in Hawaii, in the Southern, and in the Great Lakes. So for this, we see a huge potential. However, the stage of the offshore wind industry in the US is still in a very nascent stage. So up to now, the only fully operated offshore wind farm in the US is only 30 megawatt at the Block Island. However, if we look into the future, people already have a pipeline of building total of 25 gigawatt of generation capacity by 2035. And if we look into the year of 2050, the Department of Energy set the goal to have 7% of the total electricity in the US is generated from the offshore resources. So in order to capture the trend, the industry, the US, the industry has to be pushing toward a bigger wind turbine. So for example, if we look in ABB, they have a 7 megawatt version. The Siemens Gamesa, they have 10 megawatt. The Vestas has 10 megawatt. And GE, they even go further to 12 megawatt direct drive. So let's look into the common power conversion architecture of these high power wind turbine. So we have a wind turbine producing mechanical power, and we need to deliver that mechanical power into the electric power grid. The grid could be a DC or an AC grid. Then look at the requirement. We have the wind turbine needs to operate in variable speed and operate in a limited speed range, and it needs to deliver multi-megawatt power. And this power needs to be delivered to the grid. So the grid also needs to absorb multi-megawatt power. And at this power level, we will foresee to have like in the kilovolt of the voltage and the kiloamps of the current. And that is a job of the energy conversion system, including the generator and rectifier. So let's look at the commercially available, but this architecture, is it like really feasible nowadays? Let's look at some limitation of the switch. It especially comes from the rectifier. So the rectifier, we see that in the rectifier, it's nowadays heavily rely on the insulated gate, heavily rely on IGBT. And when we look into the voltage and the current rating of the IGBT, we see that is mostly in the region up to 6.5 kV and 2.3 kiloamp. And when we design a power converter, we also need to derate this value. So the switch itself is not sufficient to provide like 10 megawatt of power in the region that we want to operate at. And if we look at the diode have a wider range of the voltage and the current. However, the topology based on the diode doesn't allow you to control the power flow, although it has very high power capability, high reliability, high power density, and high efficiency. So in order to control the power flow, we need to use the two-level converter based on IGBT. But when we go to the active switches, then we can control the power flow, but the power capability will reduce because of the reason I just presented in the previous slide. The voltage and the rating capability, the voltage and the current capability of IGBT is way lower compared to the diode. There are other work in other topologies like neutral point clamp and flying capacitor, which increase the power capability, but you also increase the number of the switches, so the simplicity of control will be decreased. And the question we are trying to answer now is there a different way we can look at this problem and utilize the commercially available switches today to achieve the power level that we want to? And that is the topic for the talk today. And for the talk, to address that topic, I will go through three discussions. The first is about the integrated generator-rectifier system. And the second is the power flow control and MPPT particularly for this system. And then we'll illustrate some simulation and some experimental results to illustrate the point. So let's look at the integrated generator-rectifier system. Before the conventional way of doing power conversion, we have a fundamental approach we call the collect then process. It means that all the mechanical power will be collected on the generator, and one single AC port will deliver all the power to the passive to the rectifier. However, at the high power level, we say that we have multiple windings inside the generator. Why not we just take multiple AC port out of that generator and then process that amount of power by the rectifier, and at the output of the rectifier we will collect the power like at that stage. So if we approach a problem using that method, two key advantages will arise. The first one is you don't have to design the converter for the full power of the generator. So you can utilize the available, the commercially available switch to design the converter. And the second is you can combine different types of converter to achieve better conversion efficiency. For example, here we combine the active rectifier and the passive rectifier. So here's the illustration of the benefits. Because you only use one active rectifier, so most of the power will be processed on the passive rectifier. Then the consequence is you will reduce the size of the active rectifier. So for example, we consider an example of the system rated for 3 megawatts. If you use conventional approach, then the active rectifier has to be rated for 3.65 MVA. But if we do the approach that I just mentioned, and we pick the number of AC ports to be 3, which is the optimum point here, the active rectifier only need to be rated for 2.8 MVA. So that is about a 23.6% reduction in size of the active rectifier. That could help you to reduce the cost of the power electronic system. And another key benefit is because we're shifting most of the power to the diode rectifier, which doesn't have switching losses. So you improve the conversion efficiency across the whole operating speed range. So for example, we look here, the dotted line is a conversion efficiency for 3 megawatt system using the conventional approach, which is collect then process and approach. And the solid red line is the conversion efficiency using the process then collect the fundamental. And at the rated condition, we see that is 47 reduction in the conversion loss. So in order to capitalize these two key features in the offshore wind turbine applications, we need to have the maximum power point tracking. This is the reason why. Because wind turbine is a mechanical system, and the power output of the wind turbine is depending on the rotational speed of the wind turbine. So for example, for the wind turbine we are considering, if the rotational speed is about 1.7 radian per second, consider wind speed to be 12 meters per second, the output power will be at 3 megawatt is the maximum power. If it spins a little bit faster, then the power will reduce. Or if it spins a little bit lower, then the power will reduce as well. So, but the wind turbine doesn't automatically just rotate at the maximum power point. You need to have a power electronic system that can control the amount of power you draw out of the turbine to force the turbine to rotate exactly at the optimum speed to have the maximum power. So that is the reason why the power electronic system need to be able to perform maximum power point tracking to capitalize the benefits that I just mentioned. So when we look into this architecture, it seems to be difficult to control the power flow. The reason because of the appearance of passive rectifier comprises of diode in the system, and we all know that the passive rectifier, you cannot actively control the power of the passive rectifier. But in this work, we will show that actually we can achieve the power flow control using this architecture. And the key behind that, because we have a series connection, we have an active rectifier at the bottom of the system, and using the active rectifier, we can control the power flow. And this diagram will illustrate my that key point. So if you consider you want to control the power going to the DC bus, and the DC bus is already constant value that is maintained by the grid interface. So if you could control the amount of current flowing into this DC bus, then you can control the power flow into the DC bus. And for our architecture, we consider the top to be the passive rectifier. The voltage output of the passive rectifier is already pretty much determined by the rotational speed of the wind turbine. So the voltage on the active rectifier is almost constant because it's just the difference between the DC bus voltage and the passive rectifier voltage. And we look at what control knob we have for the active rectifier. That is the D-axis current on the AC side. And if you look at the power balance equation down here, the left-hand side is the amount of power going out of the AC side. And the right-hand side is the amount of power going into the DC side. And if you look at this condition, VA, as I argued before, it's almost constant. And ESD, that is almost constant dependent on the rotational speed. So what you really have control is the ISD, which you have control for the active rectifier. So this relation set up, which is say that, oh, using the active rectifier D-axis current, you can control the DC bus current and consequently the amount of power going to the VDC. So this diagram is a little too many things to see, and we can build an abstraction on top of that. So you can model the DC bus voltage by a constant voltage source. The passive rectifier is a voltage source, and the active rectifier by a current source. And this current can be controlled using the D-axis current. Okay, so this is very simple model, but that accurately predict the relationship between the D-axis current of the active rectifier and the amount of power going to the DC bus voltage as illustrated here. So we consider a system at 3 megawatt, and this is the active rectifier D-axis current. So when the system is rotating at the rated speed, you will corresponding to the red line here, you will see that by changing the D-axis current, you can control the amount of power going to the DC bus following the red line. When the generator is rotated at a lower than the rated speed, you can still have the power control capability. And when it rotates higher than the rated speed, you still have the power control capability. So, and this is, in order to control the D-axis current, we use the standard PI controller with feed-forward terms. And following this diagram, this is sort of standard, so I don't go too much details in here. So the take from here is, okay, we have the D-axis power of the current of the active rectifier, and we can control the power going to the DC bus. And the question is, how do we use that for maximum power point tracking? And this is illustration. If you have a wind turbine and the wind speed is fixed, the power output of mechanical output power of the wind turbine will follow the blue curve here. So if you control the DC bus power, follow the dashed orange curve like I draw on this side. The clamp is the wind turbine will automatically operate at the maximum power point. This is the reason why. If you look into the left region, the mechanical power is higher than the electrical power. Then you have a excess power to speed up the wind turbine. And when it passes the maximum power point, then the electrical power will be higher than the mechanical power. Then it slows down. So this way it's automatically settled out at the maximum power point. Okay, so this is the heart of my presentation here. And after this, when have the method, we just need to add the power controller and the maximum power point tracking algorithm outside of the conventional current controller, and then we can achieve maximum power point. And I illustrated using the next point in my presentation, which are the simulation and experimental results to illustrate the MPPT. So the simulation, first we want to validate the model that we built for power flow control. And we do that by build a simulation model with 3 ports, permanent magnet synchronous generator, the top 2 port power passive rectifier, and the bottom port power and active rectifier. In this simulation, we incorporate the switching dynamics of the active rectifier to really illustrate the point. So this is the result. We will keep the Q-axis current at 0 and making some steps in the D-axis current of the active rectifier. And for the reason of power balance relationship, when you step the D-axis current, the DC bus current will change as well. It's following some steps here. And the consequence, because of the DC bus current change, the amount of power you put into the DC bus will change as well. So this result validates that even when we incorporate the switching model of the power electronics, we can achieve the power flow control into the DC bus. And with this, we go ahead and put on the turbine mechanical power and the MPPT controller. The turbine mechanical power will measure the DC bus power and decide what speed does the turbine rotate. And the MPPT controller will measure the current speed of the motor and determine what is the D-axis current it needs to regulate the wind turbine to operate at the maximum power point. And this is the result. So just a reminder that this is the mechanical power, and we want to operate exactly at the point of 3 megawatts and around 7.2 RPM. And this is the time plot of how much power going out in the DC bus. So you see that the power, the actual power in the DC bus follow the blue curve and eventually will converge to 3 megawatts. And the actual speed will converge to 17.2 RPM. It means that we successfully put the turbine to operate at the maximum power. And this is how the current looks like. We successfully keep the Q-axis current at 0 for unity power factor operation. And the D-axis current is adjusted by the current controller in order to achieve the maximum power point. So on simulation, we succeed in illustration of our method. And we go to an experimental setup. And this is the setup in the lab. So what we do is we have a generator set comprises of 3 ports, port 1, port 2, and port 3, and a prime mover. The role of the prime mover is to emulate the wind turbine. And for port 2 and port 3, we feed 2 passive rectifiers, and port 1, we feed an active rectifier. Output of the rectifiers are series connected and feed to a power electronics load operating in constant voltage mode to mimic the grid interface. And the active rectifier will perform MPPT. And those two curves illustrate our control strategy. We program the prime mover to follow the dotted orange curve, which is the turbine power. And we program the active rectifier to deliver power to the DC bus following the blue curve. And this is the result. We see that the optimum speed here will be 140 RPM, and the optimum power you want to operate is 25 watts. And here's the speed trajectory of the generator. Eventually, it converts to the optimum speed. And then we look at the DC bus power is the amount of power, 25 watts delivered to the DC bus. So this way we claim that, oh, we actually operate exactly at the maximum power point. And with this slide, I want to conclude my talk with 3 points. The first point is we do have an integrated generator rectifier system that can reduce the size of the active rectifier and have a lot of gain in conversion efficiency. The second point is we build an equivalent circuit model that predicts the relationship between the D-axis current of the active rectifier and the amount of power going to the DC bus. And using this model, the last point I want to illustrate, it will successfully achieve the maximum power point tracking for the wind turbine. And with this, I want to conclude my talk, and I'm open for questions and answers. No question? Yeah.
So can you go back a couple slides where you're showing the unit reports?
Yep.
A machine that you would actually deploy.
How does it translate to a machine?
Yeah, I'm imagining a wind turbine, right?
Yeah.
I'm not picturing 3 machines like that as the most efficient way of setting that up.
Yep, it will not be. So the reason we set up this one because we can buy the motor off the shelf and we just stack them up, and that is a simple way to implementation. But if you look into the rotor structure of the stator structure of each motor, it has multiple teeth coming out, and on each teeth, it has a widening across each teeth. So we can, in an actual generator design, we can make one group of teeth go to the passive rectifier and another group of teeth go to the active rectifier. That way we can integrate everything on a single generator. Yeah.
That's more along the lines of what I thought you presented in the past. You must not have told people that here.
Yeah.
Otherwise, well, you're going to get that question.
Yeah. Thank you, Andrew. Yes.
So if you're having some go to passive rectifiers and some go to active, then I imagine at like different points circumferentially around the motor, you'll be pulling different power.
Yeah.
And that could create like interesting thermal situations where one area gets more thermally stressed than others. Have you thought about that or how it would influence lifetime or anything?
Yeah. So we are still in the process of designing a generator, and the thermal aspect will be considered in that phase of the project. But I can give you some initial thought at this point. So first, for one active, so for example, we take from this figure. For one passive rectifier, you may have to series connect multiple teeth to power one passive rectifier or one active rectifier. Then you don't have to connect the teeth next to each other. You can distribute it along the air gap to have a more uniform thermal distribution. The second point is about the thermal. We see that, of course, there's a mismatch between the amount of power coming out from active rectifier and the amount of power coming out of the passive rectifier. But that we need to have some design consideration to make the port providing power to the active rectifier be able to handle that power mismatch. So that is the design consideration for the generator.
In your setup, you showed 2 passive rectifiers and 1 active rectifier. I have several questions. So earlier on, you talked about how IGBTs have a sort of like a smaller range of voltage.
Yeah.
Whereas the diodes can handle much larger voltages.
Yes.
So I was wondering, in this setup, it seems like the voltages would be divided in 3 ways, right?
Okay. You refer to this graph?
Yes.
Yep.
But then in the next, you can go for. Yes, you can go back. So in this slide, so they're just 3. So I'm guessing the active rectifier will be built with IGBTs, correct?
Yes.
Yes. So which means you're looking for kilovolts at the end. You'd have to distribute the voltage across the passive and the active in such a way that each passive rectifier is able to handle more voltage than the active rectifier. Is that correct?
It is close. So if we see that, if we combine the voltage of all the passive rectifier.
We have class right now. Sorry.